Hey guys, so today we're talking about completing the square. This is a fairly specific technique from algebra. It has to do with quadratics. Some quadratics are already perfect squares, and so you don't need to do this, but then for most that we're going to see, there's something kind of missing there to make it a perfect square, so we have to add something to it to complete the square, as we'll see. So I'm going to run through some examples. I think I have 6 examples altogether today, and then I'm going to kind of go through a backwards derivation of why it works. Of course, this is going to be on YouTube. I tend to go somewhat fast sometimes, so you can always pause, rewind if you need to see something, and I very much encourage practicing this as well, because math is very much a skill that requires practice, really. So I encourage you, if you see a problem, once you understand the process, pause the video, try the procedure yourself, and see what kind of lines up with what I do. So by the end of these 6 examples, hopefully everything makes sense. So I think we're just going to jump into the first example here. What I've called step 0 here is not always necessary. The leading coefficient is the coefficient of the square term in our case. So this one is just 1. There's nothing to factor out here, so that's why I called it step 0, because we don't always have to do this. So in this case, there's nothing to do there. And actually, one thing I like to do here first is take the constant term. I'm going to just move it over a little bit to make some space for some other terms. So we got x squared plus 6x. That was a minus 3. I'm going to put it, say, I'll put it right here. That works. So it's still all there, but now I've got some space because I'm about to add some other terms. So first thing we're going to do, step 1, it says half. We're going to take half of the coefficient of the linear term. So in this case, you've got 6 here is the coefficient of the linear term. I'm going to draw some arrows like this. This is kind of how I like to do this. So half of 6 is 3. And that's kind of an intermediate value. That's why I put it off to the side. We don't need it yet. We will need it in a minute, but I put it off to the side here for now. Step 2 is squaring it. So we've got 3 now. 3 squared, or 3 times 3, is just 9. So I'm going to put that up there. I'm going to add it to the rest of it. Thing is, I can't just add things to quadratics or functions or whatever whenever I want. If I add something, I have to subtract it as well. So I'm going to say minus 9. So I've effectively added 0 there. So nothing's changed. So that's it for step 1 and step 2. Next step, step 3, now this 3 here is going to be part of our answer. So we're going to wrap this 3 with that structure here. So we've got x plus 3, everything squared here. And what that does is it's really, now, and the reason we picked this 9 here to add is because now these 3 terms are a perfect square. We're going to see that a lot more later. That should make sense near the end of the video, I think. So I'm going to circle these here. Basically what I've said is all of these 3 terms get condensed or factored into just this package here. So that's where all those 3 terms went. They went into there. The only last thing I have to do now is account for the last 2 terms there. There's a minus 3 or minus 9 and a minus 3, and that's the last step. Step 4, simplify. So negative 9 minus 3 is simply negative 12. This is a little bit messy how I've written it here, so I can clean it up a little bit if I want. I'm just going to rewrite everything. X plus 3 squared, and then minus 12, and that would be my answer to this problem. So we completed the square, and we factored it into a perfect square there, and we've got some leftover bits. So that's it for completing the square on that one. So I think we can move on to a second example. X squared minus 8x plus 10. Plus 10, and again, I'm going to move this 10 over here so we have a little bit more space for a couple of extra terms. First step is to factor out the leading coefficient. There is no leading coefficient here, so we don't need to worry about that. Next, we take half of the middle term, or the middle coefficient. One slightly tricky thing here is we have to keep track of this negative here. So half of negative 8 is negative 4. Of course, once we square it, it's going to become positive now. So negative 4 squared is positive 16. But then, so I'm not just adding anything I want, I have to subtract off 16 also. So that was steps 1 and 2, half and square. Next, I wrap my negative 4 with that. And actually, in this case, I don't need the plus because there's already a minus there. So I can just kind of wrap it in that. I could put a plus if I want. It'd be plus negative 4 if you want, but I'd say just simplify it to this. And then lastly, that takes care of the first 3 terms. The last 2 terms are negative 16 plus 10, or 10 minus 16, which is simply negative 6. And that would be my answer there. So x minus 4, all squared or quantity squared, minus 6. So that's it for example 2. Okay, so x squared plus 5 halves x minus 1. And these numbers, these coefficients can be anything. The technique should still be the same, and it should still work. So we're going to start by factoring out the leading coefficient. There is no leading coefficient, so we're good there. Step 1, take half of 5 over 2. Half of a half is a quarter, so half of 5 halves is 5 quarters. Or if you want to, you could see that by taking 5 halves divided by 2, which we know this is 5 halves times 1 half, and you multiply straight across, you get 5 over 4. So quick, just reasoning there. So half of that is 5 fourths, and it's positive because there was a plus there. And then I square this, I get 5 squared is 25, 4 squared is 16, and I have to subtract that as well. So now these first 3 terms should be a perfect square. I can factor that into x plus 5 fourths, all squared. And then I need to resolve these last 2 terms, which is just fraction addition at this point. This is the same as 16 sixteenths. If I add these together, I get, what would that be, 41, I think? 40 minus 41 over 16. I'm not going to go into the details there, but that would be, if I have that right. Yeah, that looks right. 41 over 16. And then that would be my answer there. So again, this procedure works for any numbers you want, and the techniques are still the same. So the next 2 examples I have are slightly trickier, but now we just have to incorporate step 0. And the rest of the process should still be the same. So 5x squared plus 30x minus 15. So now this one, now we do have a coefficient here on the leading term, so I have to factor it out. If I factor out a 5 there from everything, now I've got x squared. You always want it to just be x squared there, so that's how you know you can proceed with completing the square. And you can think of factoring as like dividing the number out. So 5 divided by 5 is 1, 30 divided by 5 is 6, negative 15 divided by 5 is negative 3. And again, I'm going to leave a little bit of space so I can plug in some other terms there. So that is step 0, and that's all that is. So now we can just proceed with the same procedures we had before. First, we take half of our middle term. Half of 6 is 3. 3 squared is 9. So 9 minus 9. And then once we have that middle term, we can wrap it with this, x plus that squared. And then that takes care of the first 3 terms. We have to take care of the last 2 terms, negative 9 minus 3, which is negative 12. And then one last thing we have to take care of, we can't forget about this 5 out here. So I'm going to put these brackets around everything and say just times 5. We're almost done. There's one more thing I think I want to do. I don't like this like kind of multi-layered brackets thing going on, so I'm just going to distribute the 5 in there. So I've got 5 times x plus 3 squared minus 12 times 5 is 60. So then that would be my final answer there. So once again, in this example, we have a coefficient on the leading term. So we got to factor that out. So factoring 3 out of the whole thing, you get x squared minus, now 5 divided by 3 is simply 5 thirds x. And then you have plus 10 thirds. Again, I'm going to move that over to the side to make room for the rest. That was step 0. Step 1 is we take half of the middle term. Half of negative 5 thirds is negative 5 sixths. And then we square it. 5 squared is 25. 6 squared is 36. I have to subtract that as well, 25 over 36. So now my first 3 terms are ready to be factored. So I've got x minus, I'll just put that minus in the middle, x minus 5 6 squared. And then I have to add these, which will be a little bit tricky, but we can do that with some fraction addition. So let's see. Instead of a negative plus a positive, I'm going to express that as 10 thirds minus 25 over 36. Looks like a good common denominator would be 36 because 3 goes into 36. That would turn this into 36. I had to multiply that by 12, so I have to multiply the top by 12 as well. That's 120 minus 25, 36. And it looks like that is simply 95 over 36. And I don't think there's any simplification that we can do there. So it looks like we're done. And that's positive there. So I just add 95 over 36. And then I can't forget about this 3 on the outside, so I have to wrap this all with a times 3. And then, of course, I'll distribute the times 3 as well. That would be 3 times x minus 5 sixths squared plus, now this 3, you could multiply the 95 by 3, or you can actually divide it to the denominator. Kind of do some cancellation there. So 36 divided by 3 is 12, so that would be 95 over 12. And that would be the answer to that one. So that's it for that one. I have one more example that's a little bit different. Let's see, x squared plus 10x. Now the main difference about this one's a little bit strange looking. The only difference here is we actually have no constant term. But that's okay, we can still complete the square. But in this case, there is no leading coefficient, so I don't have to factor that out. Step 1, we take half of 10, which is 5. Step 2, we square it. So that becomes plus 25. I can't just add 25, I have to have minus 25 also. Now I wrap it with, I wrap the new number with x plus that number squared. And that takes care of the first three terms. And then I just bring this negative 25 along for the ride. And in this case, there's nothing to simplify. It's done. So it's a slightly weird case where it doesn't look exactly the same, but the procedure is still exactly the same. There's actually just less simplification there to do. So now I'd like to talk a bit about why this strategy works and kind of where it comes from a bit, from maybe a kind of a backwards perspective. Let's start with numbers first of all, instead of polynomials. Numbers are called, we call them perfect squares when they are the square of an integer, basically. So if I start with, say, 16 is 4 squared. That's it. So it's a perfect square because I can find an integer squared that gets me 16. If we're going kind of backwards through that, say for example 5, I can generate a perfect square by squaring an integer. 5 squared is 25, so therefore 25 is a perfect square. What about say 7? Can you think of an integer when you square it, when you multiply it by itself, you get 7? In this case we can't, so 7 is not a perfect square. So now let's bring this into the context of polynomials. Let's start with, say, nice simple linear polynomial, x plus 5, and we're going to square it. So to square this, of course we know that squaring means to multiply it by itself. So x plus 5 times x plus 5, we have to distribute everything. For the first ones, we get x squared. We're going to have an x times 5, so that'd be 5x. Another x times 5 is also 5x. And lastly, we have 25. And now these middle two terms I can combine because they're like terms. And I can do that in one of two ways. I notice the whole thing is the same as each other, so I could call this 2 times 5x if I want, plus 25. Or I can just multiply that 2 and 5 together and I get 10x plus 25. So now what we've arrived at is what we call a perfect square polynomial, because we arrived from squaring another polynomial. And we can recognize it because we see this 5 kind of showing up in a couple places. And actually, if I want to, I could call this 25 5 squared. So whenever you see this pattern, you've got x squared over here, a number squared here, and then x times that number in the middle times 2. That's a perfect square, and it comes from this. So to get to that middle number, you can cut the middle number in half here, or you can take the square root of that. So if you can cut this in half and then square it to get 25, then you have a perfect square. If you don't get that, then you can simply add that number in, add the square of the middle number in, and of course subtract it later, but then you're going to have that part of it as a perfect square. In terms of numbers, you could say, so like if you start with 16, maybe you find it's 4 times 4, or 4 squared, and then you say, oh hey, it's the square of 4, so therefore it's a square number, or something like that. If I started with, say, 18, for example, that's not a perfect square, but I know I can subtract 2 from it, and then add 2, and now I get 16 plus 2, and now 16 is a perfect square. That gets you 4 squared plus 2. And now there's the square part of it, and there's the kind of the remnant extra part of it. So that's the idea of what we're doing with perfect squares. So hopefully this video is helpful for learning how to complete the square and why it works. And that's basically it. Thanks for watching.